بسم الله الرحمن الرحيم. الحمد لله رب العالمين، والصلاة والسلام على النبي الهادي الأمين سيدنا محمد وعلى آله وصحبه أجمعين. سعادة مدير الجامعة المكلف الأستاذ الدكتور عبد الرحمن بن عبيد اليوبي، سعادة الأستاذ الدكتور عدنان بن حمزة زاهد وكيل الجامعة للدراسات العليا، سعادة الأستاذ الدكتور عبد الرحمن بن لبيد المالكي عميد كلية العلوم، أصحاب السعادة وكلاء الجامعة، العميدات والعمداء، أعضاء هيئة التدريس، بناتنا وأبناءنا الطلاب والطالبات، السلام عليكم ورحمة الله وبركاته. في رحاب منارة العلم والمعرفة يتجدد لنا اللقاء، واليوم نحن جميعا في ضيافة قسم الكيمياء بكلية العلوم الذي ينظم المؤتمر الدولي الأول للكيمياء التطبيقية تحت رعاية كريمة من سعادة مدير الجامعة الأستاذ الدكتور عبد الرحمن بن عبيد اليوبي. وينعقد هذا المؤتمر الدولي تحت شعار الكيمياء لعالم مستدام، فالاهتمام بتطوير علم الكيمياء هو جوهر الاهتمام بتطوير حياة البشرية والمحافظة عليها واستدامتها. فأهلا ومرحبا بكم في فعالية علمية متميزة ينظمها قسم علمي متميز في كلية متميزة، هي مفخرة لجامعة عالمية متميزة يمد الوطن في كل عام بمئات السواعد الشابة المؤهلة في علم الكيمياء، ينشر أساتذته أبحاثهم العلمية في أرقى المجلات والدوريات العلمية العالمية، ناشرين لعلمهم وتجاربهم في أرجاء المعمورة، ويمتد عطاؤهم بكل كفاءة واقتدار خدمة لجامعتهم ووطنهم في جميع مستويات المناصب القيادية والإدارية. القرآن الكريم هو خير بداية لحفل افتتاح المؤتمر الدولي الأول للكيمياء التطبيقية، آيات بينات من كتاب الله يتلوها الأستاذ علي بن أحمد المزيني.
أعوذ بالله من الشيطان الرجيم. ادع إلى سبيل ربك بالحكمة والموعظة الحسنة وجادلهم بالتي هي أحسن، إن ربك هو أعلم بمن ضل عن سبيله وهو أعلم بالمهتدين. وإن عاقبتم فعاقبوا بمثل ما عوقبتم به ولئن صبرتم لهو خير للصابرين. واصبر وما صبرك إلا بالله ولا تحزن عليهم ولا تك في ضيق مما يمكرون. إن الله مع الذين اتقوا والذين هم محسنون. صدق الله العظيم.
سعادة مدير الجامعة، أصحاب السعادة، يأتي هذا المؤتمر العميق في مسماه، الدقيق في محاوره وتوجهاته، مواكبا ومؤكدا على ثورة علمية يمثل علم الكيمياء فيها ركيزة أساسية. وقد جندت اللجان المنظمة لهذا المؤتمر كل خبراتها وطاقاتها وإمكاناتها للخروج به إلى أعلى درجات النجاح إدارة وتنظيما. عن المؤتمر وفعالياته ومحاوره كلمة اللجنة المنظمة يلقيها سعادة الأستاذ الدكتور عبد الله بن محمد عسيري رئيس قسم الكيمياء.
بسم الله الرحمن الرحيم، والحمد لله والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه وسلم. سعادة الأستاذ الدكتور عبد الرحمن بن عبيد اليوبي مدير الجامعة الملك عبد العزيز المكلف، سعادة الأستاذ الدكتور عدنان بن حمزة زاهد وكيل الجامعة للدراسات العليا والبحث العلمي رئيس اللجنة الإشرافية العليا للمؤتمر، السادة عمداء الكليات، السيدات والسادة العلماء والباحثين المشاركين في المؤتمر، الأخوة الحضور. أيها الحفل الكريم، يسرني نيابة عن منسوب قسم الكيمياء وعن أعضاء اللجنة المنظمة أن أرحب بكم في المؤتمر الدولي الأول في الكيمياء التطبيقية، والذي يتشرف قسم الكيمياء بتنظيمه في رحاب جامعة المؤسس تحت شعار الكيمياء لعالم مستدام. إنه لمن دواعي سروري أن أنتهز هذه الفرصة الطيبة لأقدم لكم نبذة عن قسم الكيمياء في الجامعة. أنشأ قسم الكيمياء مع بداية نشأة كلية العلوم في العام الجامعي 1393-1394 هجرية، ويعد من أكبر أقسام الكلية، حيث تمتد خدماته إلى قطاعات كبيرة من الطلاب داخل الجامعة والكلية وخارجها. والقسم مزود بالعديد من المعامل المجهزة للوفاء بالأغراض التعليمية والبحثية لقسم الكيمياء وللأقسام الأخرى بالجامعة. وقد كان قسم الكيمياء سباقاً إلى تشجيع البحث العلمي وتنشيطه والبدء في برنامج الدراسات العليا للحصول على درجة الماجستير منذ عام 1398 هجرية. ونحن في قسم الكيمياء نمضي قدما لتحقيق رسالة جامعة الملك عبد العزيز، والتي تحظى كما تحظى غيرها من جامعات مملكتنا الحبيبة بالدعم السخي من راعي مسيرتنا خادم الحرمين الشريفين الملك سلمان بن عبد العزيز يحفظه الله وولي عهده الأمين. ونتيجة التطوير المستمر لبرنامج مرحلة البكالوريوس، فقد حصل القسم على الاعتماد الأكاديمي من الجمعية الكندية للكيمياء منذ عام 2011 ميلادية. ويسعى القسم في الوقت الحالي للحصول على اعتماد أكاديمي دولي آخر لبرامج الدراسات العليا، على وجه الخصوص برنامج الماجستير، وذلك من الجمعية الملكية البريطانية للكيمياء. وقد أثمرت جهود منسوب قسم الكيمياء بتوفيق من المولى عز وجل على حصول القسم على ترتيب متقدم في التصنيفات الدولية، حيث احتل القسم هذا العام المرتبة 36 حسب تصنيف شنغهاي الدولي للجامعات العالمية. ولا تقف خدمات قسم الكيمياء عند أسوار الجامعة فحسب، بل تمتد لخدمة المجتمع الذي نعيش فيه عن طريق تقديم برامج خدمية للمجتمع من دورات تثقيفية وبرامج قصيرة، وكذلك من خلال الشراكات مع الصناعة لتقديم التدريب لطلاب القسم قبل التخرج، وكذلك عن طريق تقديم الاستشارات العلمية والمشاركة في الأبحاث التطويرية للصناعة المحلية وحل المشكلات الصناعية. في إطار الدور الريادي والقيادي الذي تقوم به الجامعة، فقد كانت الموافقة الكريمة من سعادة مدير جامعة الملك عبد العزيز المكلف على عقد المؤتمر الدولي الأول في الكيمياء التطبيقية في رحاب جامعة الملك عبد العزيز، المندرج تحت شعار الكيمياء لعالم مستدام، والذي يهدف إلى إلقاء الضوء على دور الكيمياء كعلم متعدد التخصصات من أجل حياة أفضل، عن طريق تبادل الأفكار الجديدة والخبرات بين العلماء والباحثين وخبراء الصناعة والطلاب والشركاء العالميين. يهدف المؤتمر أيضاً إلى معالجة وتقديم الحلول في كل من المجالات ذات الأولوية من حولنا، مثل الطاقة، الصحة البشرية، والمياه، والمواد المتقدمة، والبيئة. ونطمح في قسم الكيمياء أن يصبح هذا المؤتمر منتدى يتم انعقاده كل عامين، بهدف جعله مناسبة مثالية للباحثين في المملكة العربية السعودية لتبادل الآراء والخبرات في مجال الكيمياء والمجالات المرتبطة بها مع نظرائهم في الدول المتقدمة. يحتوي المؤتمر على 5 محاور رئيسية، هي المياه والتطبيقات البيئية، النفط والغاز والطاقة، البتروكيماويات والحفازات، المواد المتقدمة وتقنيات النانو، الكيمياء العضوية والمنتجات الطبيعية، والكيمياء الطبية. وسوف يبدأ كل يوم من أيام المؤتمر بمحاضرة عامة يلقيها أحد الأساتذة العالميين، وسوف يتبع المحاضرة الافتتاحية 5 جلسات محاضرات متوازية تنصب على محاور المؤتمر ال5 سالفة الذكر. ويختتم اليوم بجلسة تعرض فيها الأبحاث المقدمة في صورة ملصقات. هذا ويشارك في هذا المؤتمر أكثر من 400 مشارك من العلماء والباحثين في مجالات المؤتمر المختلفة من داخل المملكة وخارجها. ويصاحب المؤتمر معرض متخصص في الأجهزة العلمية التي تعتمد على أحدث التقنيات المستخدمة في مجالات الكيمياء المتعددة، والتي تشارك فيه أكبر الشركات المتخصصة في تسويق الأجهزة العلمية والمختبرات. وفي إطار الاهتمام المتناهي للمملكة العربية السعودية وما للشباب من دور كبير في بناء الأوطان وتكوين نواة لعلماء المستقبل، فقد تم الإعلان عن تقديم 3 جوائز لطلاب الدراسات العليا لأفضل 3 أبحاث إلقاء، و3 جوائز لأفضل 3 أبحاث ملصقات. وفي الختام أغتنم هذه المناسبة لأتقدم بأسمى معاني الشكر والعرفان إلى جيل الرواد من أساتذتنا والذين نشرف بوجود بعضهم بيننا اليوم، ونشكرهم على تلبية الدعوة. كما لا يفوتني أن أتقدم بالشكر الجزيل لأعضاء اللجنة الإشرافية العليا للمؤتمر برئاسة سعادة وكيل الجامعة للدراسات العليا والبحث العلمي لما بذلوه من جهد مشكور لتنظيم وإنجاح هذا المؤتمر. وكذلك الشكر موصول لكلية العلوم ممثلة بسعادة عميدها الأستاذ الدكتور عبد الرحمن المالكي وسعادة وكلاء الكلية لما بذلوه من جهد مشكور لتذليل العديد من الصعاب أثناء تنظيم المؤتمر. وفي الختام أتقدم باسمي ونيابة عن زملائي من أعضاء هيئة التدريس ومنسوبي قسم الكيمياء بخالص الشكر والعرفان لسعادة مدير الجامعة المكلف الأستاذ الدكتور عبد الرحمن بن عبيد اليوبي على دعمه اللامحدود للجامعة وعلى تشريفه ورعايته لهذا الحفل. والسلام عليكم ورحمة الله وبركاته. I will give a briefing in English for those people who speak in English. It gives me great pleasure on behalf of the organizing committee to welcome you to the first International Conference on Applied Chemistry, ICAC 2015. This conference is organized by the Chemistry Department, Faculty of Science, King Abdulaziz University under the theme Chemistry for Sustainable World. The conference will feature 2 plenary lectures, 18 invited talks, and more than 400 participants. The speakers invited to participate in this conference are eminent in their field and have a great impact in advancing their respective field. The topic of the 2 plenary lectures were carefully selected to be of common interest for a wide spectrum of scientists and audience. The conference program is rather dense, offering a considerable variety of hot topics. The conference oral program consists of 5 parallel sessions on nanotechnology, advanced material, oil, gas and energy, petrochemicals and catalysis, organic synthesis, natural product and medicinal chemistry, and water and environmental application. This, combined with the extensive and very rich poster program, makes us believe that this scientific event will allow all participants to share knowledge and experience, keeping them in touch with recent advances in chemistry. We trust that you will take this opportunity to make new friends, renew friendships, make new collaborations, and catch up on social and professional programs. I would like to extend our thanks to all of the conference session chairmen, our students who helped greatly in organizing the event, and the extremely dedicated and efficient team of my colleague in the chemistry department, Faculty of Science, who were responsible for all aspects of the technical organization and the program of this event. We are grateful to our sponsors and exhibitors for their interest and support for the conference. We appreciate very much your attendance, and we wish you a pleasant stay in our city and very fruitful conference. Thank you. Wassalamu alaikum wa rahmatullahi wa barakatuh.
حضورنا الكرام، إن إحدى سمات المؤتمر الدولي الأول للكيمياء التطبيقية هي أنه يستضيف كوكبة من الخبراء والعلماء الذين يشار لهم بالبنان عالمياً، يشاركون فيه بمحاضراتهم الافتتاحية ونتاجهم البحثي وأوراق أعمالهم التطويرية، إثراءً للعلم والمعرفة في هذا التخصص الحيوي الهام. كلمة المتحدثين يلقيها الأستاذ الدكتور مصطفى السيد من معهد جورجيا التقني بالولايات المتحدة الأمريكية.
بسم الله الرحمن الرحيم. حضرة مدير الجامعة الدكتور عبد الرحمن عبيد اليوبي، حضرة وكيل الجامعة للدراسات العليا الدكتور عدنان حمزة زاهد، حضرة عميد كلية العلوم الدكتور عبد الرحمن العبيد المالكي، حضراتي وإخواني الكيميائيين في السعودية. طبعا هذا الاجتماع من أحسن الاجتماعات الكيميائية اللي أنا حضرتها في العالم كله، ومتقدم جدا من ناحية النانو تكنولوجي، لأن دي المستقبل للكيمياء والطبيعة والعلوم كلها. يعني بأنظر هنا على الكلمات المختلفة والشغل الجميل، فأجد أنه لا ينقص شيئا عن الاجتماعات اللي أنا رحتها في أمريكا، في أوروبا هنا. فسبحانه وتعالى أعطى السعودية شيء لتساعد الشعب العربي إنه يسامر ويمشي في الأبحاث. يعني لو ما كانش السعودية في هذا الوقت وإنهم يخلوا العلم يبقى ماشي وماشي مع العالم كله، كنا بالوقت إحنا ننزل بالوقت والعالم كله الأوروبي والأمريكي يطلع. ولكن سبحانه وتعالى له حكمة إنه أعطى البترول للسعودية في هذا الوقت والبلاد العربية الأخرى علشان يساعدهم العلوم تنمو وتمشي مع العالم كله، وإلا كنا يعني هي مشكلة كبيرة، لأن العالم كله ماشي في العلوم والأبحاث بدرجة كبيرة جدا، وإحنا كنا من غير التمويل اللي بيجي من الزيت اللي هي كيمياء، هي كيمياء. سبحانه وتعالى أعطانا كيمياء تساعد الحضارة بتاعتنا إنها تمشي وتتنافس مع العالم الآخر أخرى. فأنا طبعا أتمنى للبلاد العربية إن العلوم والكيمياء خصوصا إنها يعني تمشي وتتنافس مع العلوم الأخرى. يعني أنا بنظر للكلمات للدراسات اللي موجودة في الكتاب الصغير ده، والله لا ينقص أي شيء عن الاجتماعات الأوروبية والأمريكية. دراسات نانو تكنولوجي واخدة حقها كبير جدا، وهي نانو تكنولوجي هي العلم الجديد اللي بيساعد البلاد الأخرى أنها تمشي فيه، ولو مشيت فيه هتمشي مع العالم كله. وإن شاء الله ربنا يوفق العالم العربي كله في هذا المجهود، والسعودية في أنها تساعد العلم والعلماء أنهم يتنافسوا مع العالم كله. وأتمنى لكم اجتماع ناجح إن شاء الله. وهذا من اللي أنا بقراه هنا، كل المواضيع اللي تدرس هنا لا ينقص أي شيء منها عن الاجتماعات اللي رحتها في أمريكا أو في أوروبا. فالله يسعدكم كلكم، واجتماع ناجح إن شاء الله. والسلام عليكم ورحمة الله وبركاته.
حفلنا الكريم بدعم ورعاية وحسن توجيه من سعادة مدير الجامعة المكلف الأستاذ الدكتور عبد الرحمن بن عبيد اليوبي، تشجع جامعة الملك عبد العزيز وترعى وتدعم المؤتمرات العلمية، إيمانا منها بأهمية هذه المؤتمرات في إثراء العملية التعليمية والبحثية، وترسيخا لمبدأ التعاون والتبادل العلمي العالمي الذي تنتهجه جامعتنا الحبيبة. كلمة راعي الحفل مدير الجامعة الأستاذ الدكتور عبد الرحمن بن عبيد اليوبي.
بسم الله الرحمن الرحيم. الحمد لله رب العالمين، والصلاة والسلام على سيد المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. أساتذتنا الكرام، ضيوفنا الأفاضل، أيها الحفل الكريم، السلام عليكم ورحمة الله وبركاته. تزدان الجامعة اليوم بكوكبة من العلماء لحضور ملتقى علمي متميز هو الأول من نوعه في رحاب جامعة المؤسس، فمرحبا بكم جميعا. ولا شك أن مجالات الكيمياء عامة والكيمياء التطبيقية خاصة مجال خصب للبحوث التطبيقية والتجريبية والمتداخلة مما يسهم بفعالية في تحقيق شعار المؤتمر وتوظيف الكيمياء لاستدامة لاستدامة تطور العالم. أيها الجمع الكريم، إن مثل هذه المؤتمرات هي نتاج اهتمام ولاة الأمر حفظهم الله بالعلم وتطويره وتوظيفه لخدمة المجتمع السعودي والإنسانية عامة، تحقيقاً لتوجيهات خادم الحرمين الشريفين الملك سلمان بن عبد العزيز وسمو ولي العهد وسمو ولي العهد حفظهم الله جميعاً، ومتابعة مستديمة من صاحب المعالي وزير التعليم الدكتور عزام بن محمد الدخيل ودعم الحكومة الرشيدة. أيها الحفل الكريم، إن محاور هذا المؤتمر فرصة للمزيد من أنماط الشراكة بين الجامعة والقطاعات المجتمعية، وبخاصة الجهات الراعية للمؤتمر، لا سيما أن هذه المحاور جميعها تتوافق تماماً مع توجهات الخطة الوطنية للعلوم والابتكار، مما يسهم بإذن الله في دعم خطوات المملكة نحو الاقتصاد المبني على المعرفة من خلال الأبحاث العلمية والأوراق والمشاريع المشتركة. أيها الحفل الكريم، باسمكم جميعاً أرحب بضيوفنا من خارج المملكة وداخلها، شاكراً لهم هذه المشاركة الحيوية إثراءً لفعاليات المؤتمر، والشكر والتقدير لكلية العلوم ولقسم الكيمياء على هذه الجهود المقدرة التي بذلت من أجل عقد هذا المؤتمر الدولي وإخراجه بهذه الصورة المشرفة، والشكر كل الشكر للشركات الراعية التي لها الفضل بعد فضل الله تعالى في انعقاد المؤتمر ونجاحه. ولا يفوتني أن أشكر اللجنة المنظمة برئاسة سعادة زميلنا الأستاذ الدكتور عدنان زاهد وجميع قطاعات الجامعة التي شاركت في الإعداد والتحضير لهذه المؤتمر. وباسمكم جميعا أقدم خالص اعتذاري لأساتذتنا الكرام الأقادمين من خارج المملكة ومن خارج جدة على التعب الذي تعرضوا له البارحة من جراء سقوط الأمطار، وإن شاء الله خلال اليومين القادمين نعيش جو صحي علمي ينتج عنه العديد من التوصيات لصالح الكيمياء. كما ذكر سعادة أستاذنا الدكتور مصطفى السيد، اليوم كلنا نعيش في حقل الكيمياء، فتلاحظون المنصة كلها كيمياء اليوم. سعادة الأستاذ الدكتور عدنان زاهد متخصص في الهندسة الكيميائية، زي ما أنتم عارفين أنا في الكيمياء الفيزيائية، الدكتور عبد الرحمن في الكيمياء الحيوية، فالجو كله كيمياء اليوم. أتمنى لكم إن شاء الله مؤتمر ناجح. وهذه الحقيقة اليوم تعود بالذاكرة إلى كما ذكر الدكتور عبد الله عسيري عند إنشاء القسم عام 1393-94، وبعد ذلك عندما انضممنا كطلاب لهذا القسم، ومعظم الجالسين هم أساتذتنا ولهم حق علينا كبير، علمونا التعليم الصحيح. دخلنا، طبعا أنا ماني قايل لكم متى أنا دخلت، ولكن أنا في الدفعة الخامسة، ليس في الدفعة الأولى، الدفعة الخامسة من قسم الكيمياء. فنسأل الله تعالى لهذا المؤتمر ولجميع المشاركين التوفيق والنجاح، وأعتذر مرة أخرى عن أي قصور في الإعداد واستقبال ضيوفنا الكرام من خارج المملكة وداخلها. والسلام عليكم ورحمة الله وبركاته.
حضورنا الكرام، بهذه الكلمة الضافية الوافية من مدير الجامعة يحفظه الله، نأتي إلى ختام حفلنا الافتتاحي، لتبدأ بعد 5 دقائق من الآن الجلسات العلمية والمحاضرات وندوات النقاش. نتمنى للجميع وقتا ممتعا في رحاب جامعة الملك عبد العزيز، ونتمنى للجميع النجاح في محاضراتهم ولقاءاتهم وندواتهم العلمية. والسلام عليكم ورحمة الله وبركاته.
آمين، والصلاة والسلام على نبينا محمد وعلى آله وصحبه وسلم أجمعين. On behalf of King Abdulaziz University and the organizing committee, I would like to welcome you in this first international conference on applied chemistry. I would like to welcome all our audience, our scientists, our researchers, our colleagues, and the guests. Our first keynote speaker is Professor Mustafa Al-Sayed. In few words, I would like to introduce our first keynote speaker. Professor Al-Sayed received his BSc degree at Ain Shams University, Cairo, Egypt, and his PhD at Florida State University. He was a research associate at Yale, Harvard, and the California Institute of Technology. He then became a faculty member at the Department of Chemistry and Biochemistry at UCLA until 1994, when he moved to Georgia Tech as a Julius Brown Chair and Regent Professor. Professor Sayed was the editor-in-chief of the Journal of Physical Chemistry for 25 years and is serving now on the advisory boards of the NSF and the Department of Energy in its BSAC program, and for several Department of Energy nanocenters across the USA. He and his group did research in many areas of chemical, biophysical, nanoscience, and nanotechnology. His group has over 590 publications in peer-reviewed journals, and from the citations to their work in the past decade. Science Watch ranked number 4 among academic chemistry researchers worldwide. Professor Sayed is an elected member of the U.S. National Academy of Science in 1980, and elected fellow of the American Academy of Arts and Science in 1986, an elected associate member of the Third World Academy of Science in 1984. And he was a fellow of the American Chemical Society and the American Physical Society, the American Association for the Advancement of Sciences. He is an elected honorary fellow of the Indian and the Chinese Chemical Societies. Professor Sayed received the Kingfisher International Prize in the science in its chemistry branch and a number of USA national awards. Sayed is the recipient of a number of honorary doctoral degrees from several international universities. He has also served as a von Humboldt Senior Fellow in Germany, a visiting professor at OSE, France, the Fairchild Professor at the Caltech, and visiting Miller Professor at UC Berkeley. Professor Sayed received in 2007 USA National Medal of Science from the President of USA, and in 2008 and in 2009 he received the Medal of the Egyptian Republic of the First Class from the President of Egypt. Professor Sayed is going to tell us today about the nanotechnology meets biology in the cancer cell, applications in medicine, drug delivery, and determining drug efficacy. On behalf of you, I would like to invite Professor Sayed to address his talk this morning. Thank you very much.
بسم الله الرحمن الرحيم. أولا I want to thank Dr. Abdullah for putting together such a wonderful program, very, very excellent coverage of modern research in chemistry and applications. Very, very good indeed. And as you can see, I've been involved in many meetings, and I know how hard is it to get together a group of very good scientists to have a good, successful meeting. And of course, yesterday was a very good test for us too. ربنا عاوز test us how committed are we to chemistry? So we had this rain, to put some barriers and to see how can we cross this barrier. And but I see, alhamdulillah, did not discourage us from having a very good meeting, inshallah. Somehow, because I'm using my own computer, there is you will always find the first word in the title is missing. So let me see if you can guess what the first the first word of each title is. It gets you a little bit more involved in the talk نفسها يعني إن شاء الله. يعني for example this here, fantastic, they fixed it, fantastic, very good, thank you, very good, okay. So as you can see in the program, there is a lot of talks about nanotechnology, and as you all know, of course, this is the new science that you know, about almost less than 100 years ago, the new science was chemistry. You know, before that, every chemical we want to have, we always went to the trees and got the leaves and squeeze it, and take the chemical from it. We did not make chemicals. We let nature made chemicals, and then we went and squeezed what nature has made, and that was chemistry at that time. But then, alhamdulillah, somebody showed that, hey, watch, I can make urea. Urea was the first chemical in the chemical people were able to prepare, not from the tree, make it in the lab. And that started the field of chemistry. Okay. Now, this whole new science now, that is nanotechnology, how can we, when you go down to material size to be so small, below 100 nanometer, you find that the properties of the molecule that we are used to change. It gave us new chemistry. So instead of making molecules, now we're making مواد أصغر من 100 نانومتر في الحجم. فبتختلف، تقدر تحضر حاجات، مواد جديدة لها صفات جديدة، وده اللي العالم كله دلوقتي بيشتغل فيها. إيه المواد الجديدة دي؟ فأتكلم شوية على إنك تقدر So today we will try to, one of the examples we're going to give you, أي مادة تصغر حجمها below 100, 120, 150 نانومتر، الصفات بتختلف خالص. وكل ما تصغرها الصفات بتختلف، وكل ما تحضرها بأشكال مختلفة بتختلف الكيمياء بتاعتها والطبيعة بتاعتها كلها تختلف. فيعني فتحت لنا أبواب كثيرة إن احنا نجد مواد جديدة. Okay. So today we'll talk about استخدام الذهب. طبعا الذهب حضراتكم عارفينه ان الصفة الجميلة بتاعته انه اولا طبعا ما بيصديش. It does not get ruined, oxidized or anything like that. Very stable chemical. كل اللي بتعمله الذهب، قطع الذهب، انها الضوء بينعكس منه بيبقى كويس ونضيف وما بيتغيرش وكده. ده كل الصفات بتاعته. دلوقتي اما تصغر حجمه لأقل من 100 نانومتر تجد صفات مختلفة تماما، وكل ما تحضره بأشكال مختلفة بيبقى لصفات مختلفة تانية. صفات مش بس يعني صفات كيميائيا وطبيعيا physical as well. فكل اللي هنعمله النهاردة إن شاء الله نستخدم هذه المادة اللطيفة ديت، ونحاول نستخدمها نتخلص من مرض. كل واحد منكم أكيد عارف حد عنده سرطان، لأن 1 من 4 بيموت من السرطان في العالم كله. 1 من 4، يعني 1 من 3 بيجيله سرطان. وطبعا حضرتكم أكيد اللي عارف حد بالسرطان، المقاسات بتاعتهم فظيعة جدا، صعب مرض خبيث جدا. فهنوريكم النهارده ازاي الذهب اللطيف ده اللي كان بيلمع بس دلوقتي ممكن يستخدم انه فعلا يتخلص من خلايا السرطانيه في الجسم بطريقه سهله جدا وغير مضره. فان شاء الله اوريكم النتائج بتاعته على الحيوانات اللي عملوها الاخوان في مصر في القاهره، وان شاء الله نحمد ربنا ان برضك هيبقى فيه امل ان السرطان ده نقدر نتخلص منه ان شاء الله. فالاول هتكلم شويه على النانو تكنولوجي، المواد نفسها ايه والصفات النانو تكنولوجي اللي بنجيبها منها، وبعدين هنتكلم الصفات خصوصا بتاعه الفضه والذهب لما نصغر حجمها اقل من 100 نانومتر، وبعدين طبعا نبتدي نشتغل لما ناخد القطع الذهب الصغيره ديت وندخلها على الخلايا في الجسم، الخلايا السرطانيه في الجسم، ونعرض ضوء خفيف جدا اقل من ده بس في تحت الاحمر اللون بتاعه، فقطع الذهب الصغيره دي تمتصه وتحوله الى حراره درجه عاليه جدا انها بتتخلص يعني بتسيح الخلايا السرطانيه تماما. فنوريكم النتائج، والنتائج على الحيوانات الصغيره والكبيره ابتدت الحمد لله. اوكي، كبيره شويه عليهم دي. ليه النانو تكنولوجي ان كلنا معمولين فيها قوي؟ every industry based on making material or more having useful property in human living. كل الصناعات في العالم كلها انها بتطلع حاجه من المواد اللي عندنا تستخدم في حاجه الانسان عاوزها فبيشتروها، فديت بتفتح مصانع. اوكي، اما نلاقي مواد الجديده ديت بتفتح مصانع، وبعدين المصانع بتعمل ايه؟ بهاير ناس ما عندهمش شغل بيجدوا لهم شغل، ومعظمهم طبعا بيبقوا كيميائيين طبيعيين، حاجه يعني علميا فيها شويه. فالهايرنج بيبول، الناس اللي بيبتدوا يشتغلوا بياخدوا ماهيات، صاحب المصنع بيعمل اموال كويسه، وكلهم بيدفعوا ضرائب للحكومه. دي امريكا، الحكومه الامريكيه عايشه على كده، الحكومه الامريكيه عايشه على الضرائب اللي الناس اللي بتعمل ماهيات بتديها للحكومه. فتاخد الحكومه طبعا تاخد ديت وتدينا احنا 5% بس منها نشتغل ابحاث كتير تانية. فيعني العمليه في امريكا مبنيه ان احنا لازم نلاقي مواد جديده لها صفات الانسان يقدر يستخدمها في حاجه. وبعدين جه النانو تكنولوجي قال لك ايه، تصغر اي ماده لحاجه الحجم ده هتلاقي صفات كتيره جدا مختلفه، شوف بقى هتستخدمها في ايه. وعلشان كده العالم كله والحكومات المختلفه مهتمه جدا بالنانو تكنولوجي، الابحاث في النانو تكنولوجي. اوكي، طب السبب ايه بقى ان لما المواد بنصغرها في حجم اقل من 100 نانومتر، 100 نانومتر دي قد ايه؟ سمك الشعره الواحده 15,000 نانومتر. احنا بنتكلم على مواد حجمها بس 15 نانومتر، يعني 1 من 1000 من سمك الشعره الواحده. طيب ليه المواد لما نصغر حجمها في هذا الحجم بتختلف الخواص بتاعتها؟ بتبقى ماده تانية، وكل ما نصغرها اكتر بتبقى ماده ثالثه ورابعه وخامسه، يعني جينا من الماده الواحده مواد كثيره جدا ولها صفات مختلفه خالص. ليه؟ طبعا ده فيزياء، ده فيزياء خالص. اتضح ان اي ماده حوالينا الخواص بتاعتها بتعتمد على التذبذبات بتاعه الالكترونات ديت في حجم بتاع من 50 60 70 مواد مختلفه، يبقى لها حجم معين الالكترونات بتاعتها بتتذبذب فيها، عايشه فيها، اللي هي صفات الالكترونات بتاعها، الموشن بتاعتها الحركة بتاعتها عايزة محل حوالي بتاع tens of نانومتر. فإحنا لو ناخد مادة الخواص بتاعتها متوقفة على حركة الإلكترونات فيها مثلا في 100 نانومتر، ونصغر المادة ديت ل 90 نانومتر، الإلكترونات مش هتبقى لها صفات نفس الصفات قبل كده، يصبح لها صفات مختلفة، اللون بتاعها يختلف، تعكس الضوء أكتر، تعمل أشياء جديدة جدا. فهي تذبذبات بتاع الإلكترونات في المواد، إن لما نخش في النانومتر بنخش في الحجم اللي هي كل الإلكترونات في المواد المختلفة بتمشي فيها وبتعطي هذه المواد هذه الصفات. فلو ننزل أقل من ده تبقى مادة جديدة. فيعني بدل ما نروح ندور على مواد جديدة في الجبل أو في الشجر أو كده، لا، أي مادة عندنا دلوقتي نطلع منها مواد جديدة كتير، لأن نصغرها بدل 100 يبقى 90 يبقى مواد جديدة، 70 مواد مختلفة، 50 مواد مختلفة. المادة نفسها تقدر تعطينا مواد كتيرة جدا. مهم بقى إيه؟ إزاي نحضرها وإزاي ندرس الصفات الجديدة دي إيه، وبعدين من الصفات الجديدة دي أنهي صفة تبقى مهمة في أي حاجة العالم عاوز يشتغل عليها، تتخلص من أمراض، دي حاجة مهمة جدا. فطبعا الميديكال بروفيشن ناو a lot of research ماشي في هذا الموضوع. ده تقريبا اللي بالإنجليزي اللي أنا قلته بالعربي بعد من قيمة شوية. أوكي. فتجد دلوقتي دي حاجة جميلة اللي بتوع الكيمياء، لأن تحضير مواد ده بتوع الكيمياء كويسين جدا في الحاجات دي. فتجد إن كلها سوليوشن كيمستري، كولويدال سوليوشن كيمستري. فبيعملوا مواد دلوقتي أي حاجة ما عاوزها، ومن الحجوم بس أي شكل، مش بس الحجم، تقدر تعملها بأشكال مختلفة في نفس الحجم، فيبقى لها صفات جديدة أخرى. فتجد عندنا كيوبز، عندنا رادز، عندنا تتراهيدرال، عندنا يعني عملوا من الجولد، من السيلفر. فتجد حاجات كتيرة جدا اتعملت واتنشرت، ودلوقتي بقى دراسة الصفات بتاعتها المهمة، وبعد الصفات أنهي صفة تستخدم في أي شيء العالم كله عاوزها. ديت اللطيفة، أيام زمان دي الطريقة الوحيدة علشان نلاقي مواد جديدة، نروح نفحت في الجبل ونشوف ونلاقي حاجة جديدة كده ننظفها ونشوفها إيه دي، إيه المادة الجديدة دي، هل هي صفاتها إيه. بس بتاخد 10 سنين 15 سنة على ما تلاقي مادة جديدة، ودلوقتي بقى قلت حتى عن كده. So after we do this, but now any chemist can actually prepare 3-4 new material in one afternoon. Not a big deal. But the second thing is, what are the properties of this new material? This is a big field, of course. Let me tell you what happened by the piece of gold or silver when their size goes down below 100 nanometer, for example. Okay. In the gold, there is a motion when you go to that size of the electrons, individual electrons. You put one photon in a piece of nano gold or nano silver, it excites coherently and together many electrons. Not normally, all the colors that we see here is just a result of absorption of the electron of one electron. One electron gets excited at a time to give you all these colors that we have, everything I have, everything you wear. One electron at a time. However, when you get the gold to be very small in that size scale, you can excite large numbers of electrons at a certain wavelength. It has to be a certain wavelength, coherently, so many electrons at the same time. in the small piece of nanoparticle. Now, this is a whole new property we did not have before. So, as a result of this, you create, it goes up above a piece of nanoparticle here. At the surface, it turns around. The electrons coherently turn around, come back, and then come back at the end, they go back again. At the turning point, you have very high electromagnetic fields because the light is exciting electronic motion, create electromagnetic field, which is the light, okay? Or it can make light, So that goes back and forth, and the surface create a very high electromagnetic field on the surface of the small nanoparticle. Very high intensity. Okay. This electromagnetic field, it can happen to it two things in a piece of gold, small nano gold or nano silver. It can either make light, so it gives you that one photon that you put in there, it gives you back almost 10 photons. It scatters the light very strongly. So you see light, this piece of gold, the light coming out, brilliant light coming out. Taban, this is wonderful because we can use it in Sears, Raman scattering, for example. It can image anything. This gold nanoparticle, the light coming, strong light coming out of it, it can image anything around it. And that's what we use to try to see Raman spectrum of the molecules in the cancer cell. We can put the gold nanoparticle inside the cancer cell, shine weak light in the lab, the simple scope in the lab, and put it in there. You see emission, scattered strong emission coming from the gold nanoparticle and everything around it. So you can see the Raman spectrum of all the molecules inside the cancer cell close by this nanoparticle. So you can get the Raman spectrum of the molecules that are running the life of the cell, of any cell, especially if we're interested in cancer cell. Okay? And we'll show you some results of that. And or it can just turn the light back to you in a really scattering, okay, elastic scattering. So you can see the shape of the thing around the nanoparticle, shapes, big shapes. But if you want molecules, you have to get that light coming back and analyze it with a spectrograph and see the bands, the different molecules, or the scattering from the different molecules around the nanoparticle inside the cancer cell. Or when it dies, you can tell what did it die from, how did it die. So you can actually get the secret life of the inside of a cell. It doesn't have to be cancers, any cell. So the impact on molecular cell biology will be fantastic because we can see the molecules that run the life of a cell, whether it is sick or healthy or whatever. So for the first time, we can really detect the life of cells and what happens to them. So the impact on molecular cell biology will be fantastic in the next 100 years, I'm sure. We will show you some of this. So you get. So scattering is one thing that comes from the gold nanoparticle, the small gold nanoparticle. Something else. While those electrons are being excited and going back and forth inside the cancer cell, inside the nanoparticle, they are colliding with the gold ions in the lattice of the piece of gold. So the collision with these ions give them heat, transfer some energy to it, so those ions start vibrating, and some of the vibration energy is heat, so the piece of gold nanoparticle becomes very hot, and that heat can melt the cell that you put this nanoparticle on, the cancer cell. It can melt it completely, so you can get rid of a sick cell this way. And not only cancer, any sick cell, you can get rid of it. So first, the scattering show you what happened inside the cell. Second, if you want to kill it, just don't worry about the Raman spectrum, but just shine the light back again on it, raise the intensity of the light, and it will melt the cell that you don't want, like cancer cells. Okay. Of course, you need to take the gold nanoparticle to where you want it to melt. So you put the biochemists, they gave us all kinds of molecules or peptides that can go and bind anywhere in the cell. So if you want to kill a cell, put the gold nanoparticle attached to this biochemical and mix it together with the cell solution. It will take it, the cell will take it in, it will go in and bind it to the membrane of the nucleus, wherever you want. Okay. So you can actually put it where you want to do the damage inside the cell. Okay. So, two things the gold nanoparticle will do. If it is large in size, it scatters light, so you can image where you put it. Second, if it is small, it absorbs the light and converts it into high temperature heat. And that's what can kill the cell you do not want to survive. Okay. Okay. So let me show you, here is a very interesting thing here to show you that we can see. Here is now we put silver nanoparticle inside the cancer cell. It is all over the cancer cell here. Here is the nucleus of the cancer cell, and the silver nanoparticle all over, scattered light. Let's see what happened to them. We just watch them with time. What happened to this cell that's loaded with silver nanoparticle? You can see when it turns white, like watch it, here it is. This cell is dead, died. Now watch what happened to the other cell. They go around it. But after a while, they also die. Look at, they get grouping and they also die. And what we think is happening, that the silver get oxidized, make silver oxide. Silver oxide in presence of light form OH radicals. Biochemists know this. OH radical kill cells. So silver, if you use silver nanoparticles, is not good for the cell. It kills the healthy cell and everything. So it is not a useful one to use in our work in medicine. So we tried the gold. Here is the gold, for example, gold nanoparticle. Again, has a lot of nanoparticle. You see the scattering from the gold nanoparticle. And let us see what happens here. They just, they live there, and each cell by itself, and nobody dies or anything. So that says that gold can be used inside the cell. It will not do anything unless you want it to do something. You increase the light or anything. But itself chemically is safe to use. But silver is not chemically safe for this kind of work we're going to do. First thing, we used it to detect cancer cells. If we take a blood, a patient comes to the doctor, you want to see, does this patient has cancer or not? So, this is, by the way, this is my son. He's a surgeon, cancer surgeon. And this is one of my students. They did this work. And you can see here. Let us see here. Here, this cell here, all the gold nanoparticle went and light sat down on the surface of the cancer cell. Because they have this molecule that take the cancer cell and bind to the, take the gold nanoparticle and bind it to the cancer cell, surface of the cancer cell. This is another cancer cell, and also does the same thing here. But this cell is healthy. That blood did not have cancer. So you can see here is the cell, nothing on it. The gold nanoparticle everywhere in solution, but does not bind to the cancer cell because it does not, the cancer cell surface does not have the molecule to bind to your peptide that you put there with the gold nanoparticle to bind to. So then you say, okay, this blood is safe, no cancer there, but this blood and this blood definitely have cancer. You can see one cell that is strong of the scattering of the gold nanoparticle to light. Okay. We can also you can use this scattering to determine how good a cancer medicine is. So there are two cancer medicines here, cisplatin, and the other one 5-fluorouracil. And all what we did, just bind the gold nanoparticle to it, and then we add to each one of them the same amount of medicine, cancer medicine, to kill the cell. And we watch under a microscope how long does it take for this medicine to kill cancer cells. Why? You're going to see. Once the cancer cell dies, it doesn't move. As it is dying, it's expanding in volume, scatter light, okay, but once dies, there is no motion. So here are two of them, cisplatin, and the other one is another 5-fluorouracil, and we'll watch them how long the cell is still alive, it's moving in solution. But you notice, cisplatin already died, but this one is still, this medicine still didn't kill it yet. So wait until we see how much time it will take for the cell to stand still. Once stand still, here we go, it died now. So we can see the difference in time, and they tell us the cisplatin is very, very good. It killed the cancer cell. The same amount killed the cancer cell in a very short time because the cell dies, no motion. The other one, it keeps moving for a while until it dies, so we can tell which medicine is better. Very simple method, yeah. And you can also do it optically, spectrally, and you see the size of the cancer cell. It gets bigger as it dies. Until it died, then the size become constant. Same thing here. This died here, that become constant here. So died about some here. You can also here, it dies a little bit about here. Cisplatin, yeah. So simple methods you can determine, and the method that we used give us the results about the efficacy, how good the medicine is, like what the biochemist measure it by biochemical techniques. Okay. Second thing, we got a little bit more greedy, and we like to find out actually what are the molecules inside the cell when the cell dies. What happens, okay? So we have to take now the scattered light that comes out from these cells and put it in a spectrometer to analyze the vibration bands of the molecules that are very close to the cancer cell. So we can see molecules, we can see peptides, we can see all kinds of things, okay? So here is the technique that we developed, very simple technique. All what we have to do really is, here is the cells here, when it dies or whatever happened to it, and we shine light on it, and we take the light back and we analyze it in a spectrometer. And the spectrometer gives us all the different peptides, different aromatic residues, and all these things right here. So this give us the Rayleigh scattering, the whole light coming back, which we used before, and that is the spectrum here, broad, and give you the intensity of that. But if you want to see molecules, you have to put it in a spectrometer and analyze for the different molecular things close to the nanoparticle inside the cell as it goes through life, So we done this, here you go. You can see here, this is 3 hours in the life of the cancer cell. We already put the gold nanoparticle there and scattering the Raman spectrum to us. So this is the total Raman, the vibration spectrum of the different molecules inside the cancer cell around the gold nanoparticle, okay? And as you can see right here, the cancer cells start making DNA. So you start this region, there was nothing there for the first 9 hours, but then after 9 hours, the cell the cell is trying to make two things exactly the same, and then it divides. So the one cell divides into two. But to do this, it has to make, during its life, all the different molecules that it needs for living. So the first part they do here make a lot of proteins during this time. And then start making some DNA to start making nucleus. You can see the Rayleigh scattering is making here 2 nuclei here already. 1 nucleus at this time, it starts making 2 nuclei because the nucleus take with it the gold nanoparticle. So you can see when the nuclei are splitting, okay? And then the nucleus starts getting bigger and bigger. And at this time, the cell divides into 2 cells. This is a healthy cell. We did not want to kill it. We just want to see its life itself, okay? And now the analysis of these bands here will tell us what peptides, what proteins are formed. And that is really something that very hard to do normally during the lifetime of the cell itself, because we are inside with the gold nanoparticle scattering the light to us, and the light tells us what molecules you have there, okay? And you can analyze in terms of the cycle of the cell, the different components of the phases of the cell here, and you can correlate them, and you can see here, as I said, at this time, it starts making the DNA. And then more, and then the correlation between the, one thing you should notice here, you see this spectrum here in the beginning, when the cell just was born, this spectrum here looks very much after the cell divided into 2 new ones, 2 new cells. So the spectrum have to be the same. You can notice here, all the bands here, very similar to when the cell was just born. Now the cell made 2 newly born, you can see the spectrum exactly the same. So we know that we are following the lifeline of the cell itself, from the day it's born until the day it divides into 2. Okay. Okay. Now, since we can we detect cell death? How can we detect cell death? Well, if we follow this spectrum, the spectrum is changing because it's making new protein, new compounds, and so on, and that's why the spectrum is changing. If the cell dies, chemically it doesn't make new compounds. It doesn't make new compound, that means the spectrum doesn't change. So when we see the spectrum is the same and just with time after time after time, we know that is the time when the cell actually died. And that's what we can use this to determine drug efficacy again in more detail. But more important, we can tell how did it die. Because we are seeing all these bands corresponding to different molecules formation, and therefore we can hopefully determine the mechanism of death of the cancer cell by the different chemical medicine that we added to the cancer cell. But that's just opening up new fields. I'm showing you opening up new fields. It's going to take a long time to examine different ones and so on. Okay, here is a very interesting, just to show you the idea I said. Here is we added a lot of gold nanoparticle in there. Gold nanoparticle is a chemical. If you add too much of it, it will kill the cell. Okay, and so you can see here is the spectrum start changing here, as we said before, and watch this. But from here on, you see this spectrum here is very similar to this one. This is time. This is after 10 hours. This is after 11 hours. This is after 12 hours. You can see the spectrum exactly the same even after 19 hours. I remember my students came running to me. They said, we don't know what happened wrong. There is no change in the spectrum. I told them, you tried to kill the cell died. When the cell died, there is no chemistry. No chemistry, that means no new molecules are coming. No new molecule, no new spectrum. So you know that the cell died after 10 hours. 10 hours, the spectrum become constant. That is the way to tell that the cell died from the amount of drug you put in there. This is another very accurate way not only to tell you how the drug works, but also how effective the drug is. Okay. So here, let me show you now. We're going to use it to determine drug efficacy again, how good a drug is in killing cancer cell. So we use the same 3 drugs here, and now we're looking at the Raman spectrum, the vibration spectrum. You can see here, the spectrum is changing. The cell is still alive, you know, but watch here. From here on, the spectrum remained constant. So at this time here, the cell died. No chemistry. No chemistry. So we know it took so many hours for this drug to kill the cell. The same amount of cisplatin took only this amount of time. You can see the spectrum remained constant after this. The spectrum is exact, it doesn't change. But before that, it was alive, so the spectrum is changing, molecules are new, molecules are made, but then after this, it died, and the spectrum becomes constant. So it took this amount of time to kill the cell by cisplatin. We're using the same amount of drug, of these all different drugs. This drug here doesn't do very well. Look at it. The cell lives for a long time before it died. At this point here, you can see the spectrum remain constant. That means it died about 12 hours later. So that is the worst drug. This here, cisplatin, as you guys know, I'm sure, is very powerful drug for cancer. And this one here is in between. But we can determine it very accurately and by very simple technique, actually, very simple method. And we determine the relative efficacy, how good drugs are relative to one another, and it came out to be very much like the biochemistry give the people. So you can see that the relative efficacy of the different drugs is very much the same as determined by biochemical techniques. Okay. So gold nanorods can be used for in vivo cancer diagnosis and cancer therapy. And I'm trying to summarize things a little bit here. Near infrared radiation penetrates the human body long distances. Nanorods can strongly scatter near infrared light. Thus, if conjugated to cancer cells, it can be used in cancer detection. You can detect it, that this cell is cancer, this patient has no cancer cells. It can also absorb strongly the near-infrared light and can melt the cancer cells to which it is conjugated or near to it. Okay. Oops. What happened here? What the heck happened here? My goodness, what the heck is going on here? Why? Come on. What the heck is happening? Huh?
Cancel.
That is cancel.
Don't say.
Now we are back to this. This is the talk now, is it?
Yes, sir. Yes, sir.
Ah, now we'll be getting
Double click.
and go back to where we were.
Yes, sir.
Let's see where we are here now. This is where we were. This is here. I think this was it. Huh? Then we open this one here. Yeah. Okay, well, okay. Thank you very much. Okay. Now, can we detect cancer inside the body? We know the gold nanoparticles scatter light. That means if we bring light from the front of the patient, and then we look in the back of the patient, and the light goes through and meets cancer cell that has on it a lot of gold nanoparticle, the gold nanoparticle will scatter the light back, and then you see a black spot, no light, as the size of the cancer itself. So you can see here, right here, you can see this dark spot. This is light coming from the other side of the mice, and you can see indeed there is a dark spot right there, which tell you that there is cancer there. It's scattered light back. Okay. All right, and you can see, you can also take the absorption spectrum and everything. So we know that we can actually use it to detect cancer inside the body itself. Of course, you have to be careful. The cancer, has to be in a place which everything is free. Is not some places, say in the chest and bones and all sorts of things. So it might be more complicated there. Yeah. Okay, and that is what we detected there. Here is cancer here. Now we can also detect if we got rid of cancer or not. Did we kill the cancer or not? So you can see here is cancer here, was here, then we injected with gold nanoparticle, exposed it to near infrared light. Why near infrared light? Because near infrared light goes in the body. Visible light doesn't go in the body, but a few millimeters. The near infrared goes all the way through. So if we got nanoparticles sitting on a cancer place inside the body, when it hits that place, the gold nanoparticles scatter it too much that the light coming through will be very little. You see dark spots. So we can detect how big the cancer spot is, how big the cancer is. So here you go, you can see here. And then you can also tell, did you cure cancer or not? Because you can study this as a function of time. If the size that you treated with gold nanoparticle and the light will heat the gold nanoparticle and melt cancer cells, okay, then this spot will not grow with time, no cancer. If you did not do that, then with time this thick cancer grows with time. This size gets bigger and bigger. So it depends what you see. And you can see here are two spots. There was cancer here, and there was cancer here the same size. Then we injected this with the gold nanoparticle and exposed it to light, near infrared light. It heats the cancer cells where the drug is, where the nanoparticle is. So only cancer cell will die. Here, we did not do that. We did not use light to heat the nanoparticle, and therefore it did not kill cancer cells. And then we see this part here will grow with time. This here will grow in time because cancer did not die. But this one here, where we shine light and the gold nanoparticle heated the cells and killed it, melted essentially, will not grow with time because cancer is gone. So you should see that size does not change with time. And with time, it will clean it up. The body will clean up the dead cancer cells. Okay, and you can see here the one that was treated with light and gold nanoparticle. The gold nanoparticle absorbs the light, will heat the cancer cells. You find that it does not increase with time. That means no cancer. Cancer means grow with time. However, the other one that we did not use light, we just put gold nanoparticle there, but no light. That means no heating the cancer cells. So the cancer cell did not die. So you can see this one here with time keeps growing. In fact, here it is, the growth with time. So we know now in body you can use it definitely to kill cancer cells by using near infrared light, so go through the body, and then when the gold nanoparticle is sitting, you bind it only to cancer cells. When it sees those, it will heat it, and where the cancer is will definitely melt, and you get rid of cancer. Photothermal therapy using gold nanoparticle, essentially. Of course, people say, well, what the gold nanoparticle do inside the body when you use it. Any medicine, you have to check on toxicity of the medicine. That number, I'm sure people in this field know very well that. So we start looking at where is it, and you can see that here we can follow it. It turned out it's essentially mostly the liver catch it. You can see it here, and here the spleen as well. Yeah. Okay. So it stays in the spleen and the liver, but we tested. It doesn't do much to these organs. For 15 months in the mice, nothing happened, no toxicity. The mice still healthy for 15 months. It still have a gold in the spleen and the liver, but it did not affect their life. It did not kill them. And so now the work is we have to go to bigger animals. And in Egypt, there are two groups. One group at the National Research Center and one group at Cairo University, working with people that have dogs with cancer. And the last time I was in Egypt, they all brought their cured dogs to show me that it is working, and very, very nice. But the last thing I want to show, very, very nice result actually, and that is in the National Research Center, there was a cat. Look how big the cancer was, okay, around the breast. Breast cancer for female is about 40% of cancer is in the breast cancer, okay, for women. And so they worked with it, and actually they were able, by injecting the nanoparticle, exposing it to near infrared light, were able to get rid of this huge piece of cancer there. And but more important, that when women get breast cancer and they remove the breast, they tell them, you might not get children anymore. Okay, so it's a very, very serious thing, So here they try to examine in the cat there. Would she be able to nurse? Would she be able first to get pregnant? Second, if she gets pregnant, would she be able to nurse the babies from her breasts that had the cancer? Well, fair enough. You can see here, the next slide. You can see here, 2 months after the cancer was removed, you can see actually she was able to get pregnant and got the babies, and the babies are enjoying themselves. They're still alive. Everybody is still alive there. And so was published very rapidly because that's a new result. And the reason is the treatment is not very drastic. To remove the breast, that's a drastic thing. Completely drastic thing. This here, you won't even know where the cancer was by the treatment of this, because light doesn't hurt going in the body. It get inside very easy. And you melt only the place where the cancer is, not over the whole body or the whole breast. Only where the cancer is, because you got the nanoparticle to go where the cancer cells are. You bind them to cancer cells, and therefore these are the cancer cells only will be the one to heat up and kill them. So the rest of the breast, nothing happened to it. And therefore, being such a non-drastic method, as you can see, the cat, but of course now they want to get statistics. This is a case that just work it this way, or actually this is what is going to happen all the time. So now they're working with more cats and more dogs that have cancer and see what in the breast cancer to try to get this statistically viable or not. And I think with this, the people that done all the work is my son, of course, he's the surgeon. And he the first one give us cells and cancer cells, how we handle them, how we treat them, and so on. Showa did a lot of in vivo before we got to animals, did a lot of cell work, and she did most of it. Then we got to small animals, and Megan did quite a bit of work on that. He's the one that to detect cancer by scattering techniques. He's the one that first went to show that he can actually detect cancer inside the body. And Lauren was the one that did a lot of work on this analysis of these bands, and beautiful. She's a postdoctoral fellow at Harvard Medical School now. And he is the one that built the spectrometer arrangement for his PhD. He came and got his PhD with us. And of course, she is the one that first tried to encourage my students to work with animals. They didn't want to touch animals. And she was wonderful. She's now a full professor at the University of Minnesota. And I think with this, I'd like to thank all of you for wonderful. Thank you very much. And thank Dr. Aziri for this meeting. Thank you.
Thank you very much, Professor Mustafa Said, for this wonderful, informative talk on nanotechnology meets biology in cancer cell. Because we are behind the schedule, we can take only 2 questions, one from our gent section and the other one from sister section. So please, if you have any question, raise your hand. Yes.
You might have to repeat the question for me.
Yes, sure. Who has got the mic, please? And 4 upstairs too, please.
Thank you, Prof, for this excellent lecture and excellent work.
Loudly,
My question is twofold, actually. If there is a side effect for this procedure, this is number one. Number two, there is a different kind of cancer. And
we cannot hear you. Can you say it louder?
First of all, if there is a side effect for this procedure, second, different kind of cancer, did you test this procedure for different kind of cancer or just a blood cancer?
Did you test the procedure for cancer? Did you test the procedure?
Thank you.
Test the procedure.
The procedure نفسه? How you do it?
Yeah.
Well, the procedure for the animals that they did, all what they did was they see where the lump is, where the cancer is. So it was used breast cancer, for example, very. So you see where the cancer is. All what you have to do, you get solution of gold nanorods. It has to be nanorods, not nanosphere. The problem is that many people make spheres easy. They're going to use nanosphere, it will not work because it does not absorb the near infrared. And then you use near infrared light. Why? Because it goes through the body. And then when it goes and sees gold nanoparticles, nanorods absorbs it, convert it into high temperature heat. Therefore, where the gold nanorods are, this region where the gold nanoparticles are, which are absorbed by the cancer cells. Okay? And it will heat up and completely kill the cancer cells. So it is 2 things. First, you have to inject it in the region where the cancer cells are. Second, you shine light, near infrared light, in this region. Therefore, the gold nanoparticle where the cancer is will absorb this light, convert it into heat, and the heat melts the cancer cells, and therefore the cancer disappears. So you do not cut it, but you melt it, completely melt it, and the cells are dead. That's it.
Okay, thank you very much. Is there any question from the sisters section? Any question from ladies section, please? Yes,
Hello.
please. Yes,
Hello.
please. Yes, please. Over there's a question. Please go. Yes, please. Yeah. Not working? Please open the button, the power button. Can you please change the mic over there? Until then, we can have another question here. Please.
May I ask the question? Hello. My name is Yusuf Yakci from Istanbul Technical University. I am not very familiar with the area, but I would like to know what is the driving force for nanoparticles to the cancer cells. And you also use, together with the drugs, are they combined to gold nanoparticle surfaces or so?
The use of nanotechnology in drugs. Nanotechnology, the use of nanotechnology in drugs.
What is it used in the drugs?
Gold particles.
You can, as I showed 2 methods to determine if efficacy هل ايه الدراج ده compared للدراج ده in killing cancer cells. Okay, and so we did it we did it in patient cells, and I don't know if we done it in animals, but did it in cancer cells. And all what you have to do is you mix the same amount of drug in solution where the cancer cells are, and then follow what happens to the cell living condition. Because you can follow it, because you have in there gold nanoparticle to scatter light, and when the cell is still alive, you can, as it dies, when cancer cell dies, they increase in volume. Therefore, the scattered light becomes larger and larger until it dies, and then you don't see any more increase in volume. It stands still, then you find the scattering remain constant. And that is the time you measure to determine how good the drug is. A good drug will make that time very short. A bad drug, it takes a long time before that scattering become constant. So you can just do it from the light scattering intensity itself.
Okay, thank you very much. Thanks a lot.
Yes.
A question from the ladies section?
Yes,
Any question?
I'd
Yes,
like
please.
to ask.
Please speak loudly, please.
I would like to ask: is there a hope for natural product chemists to?
We cannot hear you. Please speak loudly.
Is there organic compounds can be converted into nanoparticles? Hear me? Yes. Does organic compounds can be converted to nanoparticles?
Can what?
Organic compounds
Organic.
can be converted into nanoparticles?
Converting organic compounds into nanoparticles.
Can you what?
Organic compounds into nanoparticles conversion.
Conversion of the nanoparticle?
No, organic compounds.
Organic compound.
Yeah, to nanoparticles.
Oh, I see. Oh yeah, they, a lot of polymers, they make nanoparticles of it. In fact, actually, a lot of drug delivery is probably safer to be done to deliver it using organic compounds, organic polymers in the size of nanoparticle. And the reason is you can put, you see, why they use nanoparticles for drug delivery? A very good question. Because you can put on one nanoparticle thousands and thousands and thousands of drug molecules. And then when this goes into the cancer cell, you have very high concentration of drug molecules in the cell. The rate of killing the cell is much faster. So you can really kill cells much faster if you load it with many drug molecules at the same time. And the way to do it is by putting the drug molecules around a nanoparticle, which will take thousands of them, and get it to inside the cancer cell, and that will kill it very rapidly and very effectively.
Are they injected in the cancer cell, or can be dissolved in some solvents? Does they lose their properties of if they dissolve it in solvents?
Does it affect the property of the drug? Well, of course, you select the delivery polymer or gold nanoparticle by itself should if it affects it. The gold nanoparticle, we know, they only affects it if you shine near infrared light to it. That's the only time. If you leave it with nothing, it doesn't do. But unless you add a lot of it, then it becomes drug. Too much chemicals there, and it can kill the cell. But the amounts you use for treatment is not high enough to kill it by itself. You have to shine light on it, and only when it heats up, the gold nanoparticle, it kills the cell. But not thermally, it does not. Right.
Okay, thanks.
We would like to carry on having the discussion on this wonderful talk, but because we are running out of time and we are behind the schedule, we have to stop now. And we can have now a short break, and afterwards we can go to the small rooms for the plenary session. Professor Mustafa Said is with us, and he will be more than glad to answer and discuss any point that you may have today and tomorrow. So 11:30, we'll go back again to the seminar rooms after having a short break. Thank you very much.
Thank you.
Some announcement, please, before we leave. The main lectures now is going to be moved to the other side of the building from now on for the rest of the lectures. Tonight in the evening at about 7:30, we will have a welcoming dinner at Hayat Park Hotel near to the Intercontinental Hotel. Those people who live in the resident of the Intercontinental can just cross the road. The hotel is crossing the road only. The other people who are living in other hotels, we will provide buses to take them from the hotels to the Hayat Park for the dinner. So please be aware of these two events which we will have tonight. And now we have to move to the other seminar rooms. And because the shortage of time, I think we will have very short break, and then we will start again our lectures. Thank you very much.